Well, those certainly were some interesting ideas on aviation. What's really kind of remarkable about this is that most of those machines that we were looking at were built by people after the Wright brothers, after they had successfully built, flown, landed, and survived an airplane. But they thought it was a better idea. Today's talk is the 8th presentation that we've had. We've talked about the different careers that we have in aviation. We've talked about what I expect your generation, the next generation, to do in aviation. But for the next two lectures, today and the next one, it's about aviation itself. How do airplanes fly? And then the next lecture is how do we control that flight? So my name is Rick Orzel. I'm a special instructor at Davis Aerospace. And these are the kinds of things that we teach at Davis Aerospace. How do airplanes fly? What are the principles behind it? How do we manage to do this great thing of getting into the air and flying through the air into outer space? So those are the things we do at Davis Aerospace. Again, we don't, a lot of times it's just the principles, but it's the beginning knowledge that you need to know on what you have to do to get into these careers and to have this kind of expertise. So today it's the 4 forces of flight. Well, actually, there's only 2 forces of flight. The other forces are things that keep us from flying. And they're the things that have always kept us from flying. The 4 forces of flight classically are lift, drag, thrust, and gravity. Well, 2 of them help us fly. 2 of them keep us from flying. 2 of them we're very familiar with, okay? Gravity. And we talked a little bit about gravity, I think, in the last lecture, and how for until recently, we thought that gravity held us down to the earth, that it actually pulled us down to the earth. I'm not going to get into it today, but we'll discuss that quite a bit in class. And actually, we were wrong. There's a few things like that maybe in the last 10, 15 years, we figured out that we're wrong. Indeed, gravity is a force. Gravity does keep us on the earth, but it does it by pushing us down, not by pulling us down. The other thing is drag. Drag is pretty simple to understand, actually. Anytime we get moving, there is a force that wants to hold us back. And if you ever want to experience drag, all you have to do is lower your car window when you're going down the road, anything above 40, 45 miles an hour, and you put your hand out and you will feel your hand being pulled back. That's drag. The car is pushing you forward, and we're going to refer to that as thrust. And what is holding us back is drag. So there's 2 forces that we have of the 4 forces that we're going to talk about that actually keep us from flying. And one of those is one of those is drag, and the other one is gravity. And then the 2 things we have to overcome that, one of them is lift. The lift has to overcome the gravity, and the thrust has to overcome the drag. So that's really the problem. How do we create the thrust? How do we create the lift? And then if we're going to be talking about aerospace, there are times when the thrust actually becomes lift. If we take thrust that's going in this direction for an airplane, but point it straight up, that thrust is actually lift. And we're going to give some examples of that also. So we have 4 forces of flight. We have lift, we have thrust. Those are the things we have to create to overcome gravity and drag. So let me show you a short video that it kind of explains these 4 forces of flight, and in a way that we are actually going to use them at Davis Aerospace. We have aircraft at Davis Aerospace, and we're going to be using them. We also have quite a few simulators at Davis Aerospace, and we're going to be using them as well. But for right now, we're going to talk about the context of our flying. And again, we're going to be talking a lot about this in theory, and we're going to be using it in terms of physics. Because what we learn about flight and what we learn about thrust, we can actually use in a lot of different ways, that might not be directly connected to aviation. But this is a video that takes these 4 forces, the lift, the thrust, the drag, the gravity, and puts them in the context of us flying our aircraft. All right, so let's take a quick video of this context or forces of flight.
What is it that allows this 150,000 pound Boeing 737-800 aircraft to fly? You've probably seen these large jet aircraft before, but have you ever thought about that exact question? What makes it so this 130-foot aircraft can climb thousands and thousands of feet into the air? Is it the two jet engines, both of which produce around 27,000 pounds of thrust? Or could it be the massive 112-foot wingspan? So what is it about this aircraft that allows it to fly? Well, you're about to find out on the aerodynamics of flight. To find our answer, we'll climb into the smaller Cessna 172 SP Skyhawk. It may not be a 150,000 pound jet, but the same principles apply. Most people probably understand that on an airplane, the wings are what allows it to fly, while the propeller or jet engines drive it forward. This is a good base of knowledge for your average Joe. However, a pilot should know there's much more to it than just that. In total, there are 4 forces that act on an airplane while in flight. These 4 forces are lift, thrust, weight, and drag. We'll start with lift and work our way from there. Now, the wing itself doesn't generate lift. It's more about the shape of the wing. The wing is shaped like an airfoil. In normal forward flight, wind passing over the wing, called relative wind, is what helps the airfoil generate lift. When air is moving across the airfoil, it is forced to move faster across the top than it is along the bottom. The slower moving air across the bottom puts more pressure upwards on the wing than the faster moving air across the top. This in turn creates lift. This is known as Bernoulli's principle. So while the wings are creating the force of lift, which is pulling the aircraft up, we also have the force of thrust pulling the aircraft forward. This is created by the propeller. So you can say that lift and thrust are 2 forces helping the airplane fly. Now let's look at the other side of that, the 2 forces that counteract these 2. Those forces would be weight and drag. First we'll look at weight. The material used to build this aircraft, along with the pilot and baggage weight, known as payload, and the fuel weight, all make up gross weight. Gross weight, along with gravity, all act as weight pulling down on the aircraft. In order for an airplane to fly, the lift generated by the wings must be equal to or greater than the weight of the aircraft. If your aircraft is over gross weight, and your wings cannot produce enough lift to get you off the ground, the results can be disastrous. Under Flight Simulator 10, in the Free Flight menu, the Fuel and Payload button can take you to the settings to adjust the gross weight of your aircraft. Your payload, which is your pilots and your baggage, plus your fuel, plus your empty weight will equal your gross weight. You can see that this 737-800 is just under the max gross weight. Opposite of thrust is drag. Drag is created simply by the aircraft's existence. An object's natural desire to resist moving through a fluid, such as air or water, is called drag. The effect of drag can best be demonstrated by putting a camera on the tail of the aircraft. Now you notice that the camera shakes pretty violently. This is because of the air pushing against the camera. The camera naturally wants to flow with the air and fall away from the aircraft. But here at Gear Down FS, we're smart enough to know that if you don't strap that camera down tight, you'll never see it again. Oh. On second thought, maybe we could tighten those up just a little bit more. But what a perfect example of drag. Now, just like before with lift and weight, thrust must be equal or greater than drag in order for an airplane to fly. Okay, so let's recap. Lift is the force created by the airfoil shape of the wing. Gravity, along with the gross weight of the aircraft, acts as a weight pulling down. The lifting force, pulling up, must be equal to the weight pulling down in order for an aircraft to fly. Thrust is produced by the propeller or jet engine, pulling air through the system and moving the aircraft forward, thus creating more lift on the airfoil. Drag is the natural force of an object resisting movement through a fluid, like air. In order for an aircraft to fly, thrust must be equal to drag. So, the two rules that govern whether an aircraft is able to fly or not are thrust equals drag and lift equals weight. So, do you think you're ready to explain how this large 737-800 manages to fly? Follow along with me as I explain the aerodynamic forces acting on the 737 as it takes off. Notice right now how the aircraft is not flying, obviously. You can say that the lift generated by the wings is not equal to the weight. It is actually less than weight right now. However, once the aircraft taxis onto the runway and begins applying thrust, the relative wind, which is the wind passing over the airfoil, increases, thus producing a stronger lift effect. Okay, so the 737 is applying power, creating more thrust. Right now, thrust is greater than or equal to drag. However, lift is still less than weight at this point. With enough speed, the relative wind flying over the wings is beginning to create lift. While we begin to rotate, you'll notice that we are not quite lifting off the ground yet. This is because the lift force is not quite yet strong enough to get us off the ground. However, it doesn't take long after that point for lift to be greater than or equal to weight, therefore lifting us off the ground and getting this giant beast into the air. As long as these two rules stay true, the aircraft will continue to fly and safely reach its destination. This has been Garth with Gear Down.
All right. So a lot of the same thing. The lift has to overcome the gravity or the weight. The thrust has to overcome the drag. Well, how do we do that? Well, let me tell you something. This whole thing of aviation, just about everything that we do, whether it's in the propeller or the engine or how we control it or the lift or the drag, it's got to do with creating and then managing air pressure. Everything that we do. Even when we talk about the environment on the inside of the aircraft, a lot of time that is air pressure. As we get into this further and further, we're also going to find out that there's a connection between air pressure and air temperature. We can actually control the temperature of the air by using pressure. So there's a lot of things that we can get into. And at Davis Aerospace, one of the things that we're going to learn is the language. Now, in this video, there were some terms that you heard. You heard relative wind. You heard angle of attack. You might have, at Davis Aerospace, we're going to teach you about chord line and camber line. Chord line meaning the angle of the sweep of the wing, and the camber line, the thickness of the wing. And again, different kinds of wings can create, some of them create lift for high speed. Some of them create lift for low speed. So there's different kinds of wings, different kind of purposes. That's the stuff that we get into. But everything that we're going to do, everything we talk about is how we create and then manage air pressure. Now, at the beginning of this presentation, our little entrance video, were a bunch of people and airplanes that were trying to fly, and they weren't very successful at it. So what I'd like to do now is kind of show the second half of that. And I'm going to stop it intermittently, and I'm going to ask you, what's missing here? We know that we have gravity, we know that we have drag, and we know we have to overcome the gravity, and we know we have to overcome the drag. So let's take a look at this video, and I'm going to pause it, and I'm going to give you the chance to formulate some ideas in your head. What's missing? Why are these engines, or why are these aircraft not working? Again, I'm going to pause it. I'll talk through it a little bit. And why are these engines, or why are these aircraft not working? Now, we're going to take a look at some rockets a little bit later on that are much larger than this. And again, in early aviation, we thought that rockets might be a way of propelling aircraft. And we did get into this later on. This is a very early attempt, and you can see it's in the wintertime someplace. And we're going to see that it's probably not going to be very successful. Why not? All right, so that aircraft had wings and they had a little launch pad, and it did show some thrust even after it came back down on the ice. It was kind of scooting along. But do you think that it had enough power to push the aircraft not only through the air, but because it was pointed up, it was actually going against gravity? So in this case, that airplane didn't work because they had it pointed too much in the up direction. That rocket had to not only create thrust to overcome drag, but it also had to create lift to overcome gravity, and it simply wasn't strong enough. Now, what we're going to see here is this poor fellow is going to strap some rockets to his back. He doesn't even have any wings. This is strictly rocket engines to try to propel him forward. Let's see if this works. What do you think? So if we go back to this guy, the second time he actually did get going, but again, the balance was off. All right. He did have a lot of thrust on his back and he ended up taking it. So but here he did show that these rockets worked. In the second attempt, here he's kind of on fire, didn't work very much, but if we watch closely on the second attempt, the rockets actually worked. All right, here we go. Next thing is a helicopter. Now, if you guys have gotten to know me at all, you know that I'm a helicopter mechanic at heart. And I basically think helicopters are like the coolest thing ever. And in this video here, it actually shows a very early helicopter. But I got news for you. This guy, and we're going to show that it doesn't work very well. But this is kind of another lesson in aviation, that a lot of the ideas that we had a long time ago turned out to be very good ideas. We just didn't have the technology yet to make them work, because later on, Bell Helicopter and Sikorsky Helicopter made this idea work, and it works very, very well. But let's see why it doesn't work here. Let's go back to these two helicopters here. They had lift, but they didn't have control. And here, again, you might ask yourself that question about thrust and lift. Here, we actually have propellers that have thrust that would normally be pulling the aircraft forward, but in this case, they're pushing the aircraft up. And I did this for a reason. We're going to talk about some more rockets later on that they do provide thrust, but the rockets also provide all the lift. Here, the problem isn't enough lift, it is control. You can see that they were actually picking this thing up off the ground, but they weren't controlling it well. Again, we've got to talk about Bernoulli's principle. We're going to talk about how we control this. So here, the problem isn't that the rockets that we didn't have enough lift. It was a matter of controlling it. Well, what was the problem here? Well, again, we have to create pressure. And we do that by either having air go over the wing or wing going through the air. You know, that's something, again, we're going to talk, if you come to Davis Aerospace, we're going to talk about relative wind, and there's two ways that that wing can actually provide lift. One is to have a fixed wing on the airframe and take the whole airframe through the air, so the air is going over the wing. And then in a helicopter, the wing is actually going through the air where the fuselage is stationary, but it's being whooped around. Now, this was an attempt at an early helicopter, and obviously it didn't work. Did it have enough power? Did it have enough power for thrust? It probably did, but it probably did not have enough area. In other words, to create the lift. Here we had power for thrust probably, but not enough aerodynamic force to actually create lift. Oh, this guy has really got an imagination. He's just going to become a Birdman. Now, actually, here again, a pretty good idea. It didn't work out, but later on, this is an idea that later on was used by another aircraft manufacturer, another helicopter manufacturer, and they actually got this idea working very well. Well, what's the problem with it right here? Do we have enough airspace, enough wing to create lift, or enough power, or not enough power to push the wings around? Well, I think in the last one, they probably just didn't have enough power. And you, students, you guys can go ahead and YouTube all sorts of things and see that there were a lot of very early attempts in aviation that did not work out very well. And one of the fun things that you can do is watch these and figure out why. Which one of those, we have four forces. We always know that gravity is going to hold us down. We always know that the drag is going to hold us back. Do we have enough power to create thrust? Do we have enough wing to create lift? Again, this is always a situation where we are creating and then managing air pressure. Creating and managing air pressure, creating and managing air pressure. How do we do that? It sounds simple. I mean, if you just blow on your fingers, that you're creating a little bit of air pressure, but that's not nearly enough to go flying. You can actually feel that. It does create a little bit of pressure. In the classroom, we might do a couple of things. We actually build a wind tunnel, and we create our own airfoils, and we measure the lift, and we measure the drag and things like that. We do that in class, okay? We're going to learn things like angle of attack. We're going to learn things like chord line and camber line of the wing. And then like in the next lecture, we're going to talk about how we control all that. But let's take it. I want to show you another. Let's talk about Bernoulli's principle. Now, Daniel Bernoulli was a fella that I think he was Swiss, and around the turn of the century, he came up with this idea of, and I'm going to give it to you right now, increase in velocity. This is basically Bernoulli's principle that anytime there's an increase in velocity, an increase in speed, there's a decrease in pressure. A decrease in pressure with an increase in speed. He figured that out, and then he tested it and he proved it. Well, air pressure, that's what we need to have. That's what we need to create in order to have lift. And we can do that by speed. Well, how do we make speed? Well, we can make a car go down the road. That creates speed. We see that an aircraft goes down the runway to create speed. If we're watching a helicopter, we're watching those rotor blades going around. That's speed. Anything moving through the air creates air pressure. Now, I didn't say positive or negative air pressure, because actually you need both. Anytime you're creating an area of positive air pressure, you're also creating an area of negative air pressure. And that's how we control it. We can control the positive against the negative so that they can equalize each other out if we don't need anything. And then we can really decrease the positive or increase the positive depending on where we need it. We do that all the time. And that's what our next lecture is going to be about, how we control it. So I've got another video for you, and this kind of explains the very basic thing. We need a wing, and we need that wing to create lift. We need that actually more than thrust, because we can always go down a hill, and a lot of the very early flyers, the Wright brothers included, they built gliders without engines and without thrust, because they were first working just on the problem of lift. Once we get that figured out, now let's figure out the problem of thrust, and they did that too. But first, they tackle these things one at a time. So let's look at this next video, and it explains Bernoulli's principle and lift. Then we're going to talk about some thrust.
I'm an explainer at the National Air and Space Museum's How Things Fly gallery. And today I'm going to talk to you about lift. I'm standing in front of the Spirit of St. Louis airplane. It was flown in 1927 by Charles Lindbergh, and it was the first successful solo flight over the Atlantic Ocean. Now, how was this plane able to generate lift? How was it able to stay in the air? Now, I can explain that using this airfoil here. An airfoil is like a cutout or a cross-section of a wing. So if I were to take a wing and slice it into pieces like a loaf of bread, this would be one slice of the wing. Now, if we compare this airfoil to the Spirit of St. Louis, we'll notice they have very similar shapes. They have curved tops and flat bottoms. An airplane's wing will be shaped this way because of something called Bernoulli's principle. Daniel Bernoulli was a Swiss mathematician who studied the movement of fluids like air and water. And he realized that a faster moving fluid will have a lower pressure, while a slower moving fluid has a higher pressure. Now let's apply this to our airfoil, or to a wing, so that when the plane starts flying and air hits the wing, you're going to get faster moving air on top. It's going to speed up because of the curve. At the bottom, where it's flat, you're going to have a slower moving air. It's not going to be as fast as the air on top. That slower air is high air pressure, and the faster air is low air pressure. That high air pressure pushes up on the airfoil or up on the wing, and that's why something as heavy as an airplane can fly. Don't believe me? Well, I have an experiment we all can try at home with a single sheet of paper. If I were to place this paper beneath my lips and blow, would it go up or would it go down? Let's see what happens. We notice that the paper goes up. And the reason why is because of Bernoulli's principle. When I blew my fast air on top of the sheet of paper, it was a lower pressure than all of the air in the room, because the air in the room is slower than the air that I was blowing. So that high air pressure works from beneath and it pushes up on our sheet of paper. And the same thing is happening to an airplane's wing. And that's why something as heavy as an airplane, like the Spirit of St. Louis, is able to generate lift.
Well, that doesn't seem very difficult. Increase in velocity. In other words, when this young lady was blowing the air, it was the fastest moving air in the room. So the rest of the air pressure in the room was higher because the air velocity was slower. And then as she increased the air velocity over the top of the paper, that pressure actually became lower so that the paper moved up. That's how it works. That's how it works on everything, though. So that is the key right there. That increase in velocity causes a decrease in pressure. And then the other thing that she said, too, was that a decrease in velocity causes the pressure to go up. And on that wing, when the air is hitting the bottom of the wing, it is actually decreasing the velocity. So it's increasing the pressure. So it is actually holding the wing up with higher pressure from the bottom, and it's pulling the wing up with lower pressure on the top. Well, that's pretty cool. And that's how an airfoil works. Well, let's go back to rockets here for a minute, because again, Davis Aerospace does teach aviation, but it also teaches aerospace. And aerospace is the rockets that go through the atmosphere to go into outer space. There's been a lot of really neat work that's been going on in this lately. Next video I want to show you is the Saturn V. Now, this is a rocket ship that actually sent our astronauts, the Apollo 11 astronauts, to the moon. It didn't have any wings. So they take it off and they fly it through the atmosphere by pointing the rocket up. so that all the thrust out of the rocket is straight up and it's actually lift. And that's what we call thrust vectoring. If we have thrust like this airplane behind me, the ATR-42, it has thrust that goes from the front of the airplane to the back of the airplane. If we were to take the airplane and put it nose up, now that thrust is actually lift. We don't do that very much with an airplane, at least not an ATR-42. We do it on fighter aircraft and aerobatic airplanes and things like that, but not a, this is actually an airplane that I worked on when in my career, I've worked on a lot of different airplanes. This is one of them. It's made, the 42 stands for 42 passengers. We don't send the airplane nosing straight up with 42 passengers on board. That's not done, okay. But it is done on some other aircraft. And then when it comes to going into outer space, most of the time, it's a rocket that's going straight up. But we're working on that too. There are guys that are working on space aircraft that will actually fly into outer space. Now, they're all going to be rocket powered because once you get into outer space, there's no oxygen. And we've got to have combustion. Got to have combustion? Well, what does combustion do? What does combustion mean? Combustion, that's fire, right? What does fire do? Well, it heats stuff up. Remember how I said there's also a correlation between heat and pressure? Turns out that when you heat something up, it wants to expand. And if that expansion is in an enclosed area, it creates pressure. Then we release that pressure, just like releasing pressure out of a balloon, and we have thrust. That's how a rocket works. Let's take a quick look at this Saturn V rocket. This is an older film. This is 50 years ago. This is actually not even my generation. Remember how we talked about the different generations? This is actually the tail end of the generation just before me. But this is how they got to the moon. The Saturn V rocket.
Zero, all engine running.
There was a lot of neat information on there once you start to know what you're looking for. I mean, obviously we see the flames that are coming out the back of the rocket. What do those flames do? What does any flame do? It heats things up. And when it heats up the air expands. Where is it expanding? It's expanding underneath the rocket. So we have this pocket of air underneath the rocket that's expanding. And as it's expanding, it's pushing the rocket up. But what else did we see there? We seen that rocket actually started on fire, just like the rocket that was strapped on that guy's back, or the rocket that was on that airplane. And it started on fire, and then it disconnected. We've seen all sorts of lines and hoses and things like that disconnecting. Well, why wouldn't they disconnect that before they set the rocket on fire? They did it after they set the rocket on fire. Well, it turns out that, again, because it's a rocket, it has to take its oxygen with it, and it has to take its fuel with it. Well, again, there's that relationship between velocity and pressure, and there's also a relationship between pressure and temperature. They have to take their oxygen with them. They can take a lot more oxygen with them if they freeze it. Because as you freeze something, it gets smaller and smaller and smaller and smaller. So the oxygen that they take with them is liquid oxygen, and it's very, very, very cold. Now, they don't want it to warm up. This launch takes place in Florida. Florida is a warm state. We don't, so we need that oxygen to stay very cold. So they load it at the very, very, very last moment. They're loading it right up to the very end. Those hoses are connected, okay? But then what did we see? Didn't we see kind of a steam? We seen vents coming out of there, because as soon as that oxygen is put into the rocket, it starts to warm up. And as soon as it starts to warm up, it starts to expand. Well, if it's going to expand, we don't want it to cause any failures. So we actually allow that excess pressure to come out. And that's what we see. We see these little trails of this white mist coming out. That's the oxygen. As it's getting warmer, it's starting to expand and come back out the tanks. They actually have vents in them. And then we seen look like ice. Was there actually ice falling off the side of the airplane? Well, that's bizarre. This is in Florida, and it's in the summertime. Where did the ice come from? Well, the ice came from the fact that rocket ship was so cold from the frozen oxygen and the frozen fuel that they put into it's actually like a popsicle. Now, what happens when you take a popsicle out of the refrigerator and you take the peeling off it? Remember how when you bring it out into the atmosphere and there's humidity all around it, you'll get the little frost on the side of the popsicle. That rocket ship's kind of like a popsicle, and it has all this ice on the side of it. But now we light this sucker on fire, and it starts shaking and vibrating, and all that ice falls off. So if you've ever seen any of these rockets and you wonder where's the ice coming from and why does this thing look like it's steaming, that's the answer. The answer is that fuel and oxygen has to be very cold so they can put more of it on board. And then as it starts to warm up, it vents, it expands. We don't want it to hurt the rocket, so we let the pressure go overboard. That's why we see all these little trails. And the ice is falling off because that rocket is stone cold in a very warm, moist atmosphere. So ice actually starts to form across it. And then when we light the rocket and it's on fire, it starts to shake and the ice falls off. Well, it used to be rockets like this were one-time use. All of that equipment, all of that machinery got shot into outer space and was basically destroyed. Those Saturn V engines worked once. Now, they tested them a few times on the ground, but once it went into the air, then it was only used once. And we can't afford to do that anymore. Okay, we want to send a lot of rockets, and we've seen that. I think I've showed you the video of all the satellites in outer space, and I may have shown you a video of reusable rockets, but that's what I want to show you again. Now, this time, I want to show you a rocket, but instead of it leaving the Earth's atmosphere, I want to show you a rocket that's going to land. Now, again, it's the same thing. This rocket is going to be falling from outer space. That means that it's gravity. It's pushing it down from outer space. So now the rocket is going to, instead of launching it through the atmosphere, it's going to slow it down so it lands. And we're actually doing this. Elon Musk and SpaceX has done this quite a few times, maybe up to 100 times. I know they've had different rockets that they've launched 5, 6, 7 times. Now, when we take the rocket off and it goes and it sends a satellite in outer space, turns around, it comes back and lands. And it's all done with rockets, and it's done with, again, vectored thrust. Okay, the thrust that would normally push something through the air is pointed up, and now the rocket's coming down. So let's show you this video of the rocket's landing.
The edge of Cape Canaveral in both of the side booster cameras as those are coming in.
Yes, on PY and NY side boosters.
These are actually cameras on the booster. We didn't have that back in the 70s with Saturn V. So the bottom two screens are actually GoPro cameras mounted on the side of the rocket, watching the rocket come back
They're
down.
heading towards Earth. They're about to begin their landing burns.
I want you to remember all the sound you hear in the background. All these people cheering also.
Both side boosters transonic.
And watch for the landing lights deploy at the tail end of that landing burn.
And that landing burn has started.
Both boosters looking to be on track towards their respective landing
Boosters
zones.
landing legs have started. Side boosters landing legs are deployed.
And the Falcons have landed.
LZ1, LZ2, both side boosters have touchdown. Landing operators move on to 11-1, recovery 1 and recovery 2.
Those are two of the boosters on the Falcon Heavy. The third, in this particular case, the third one was going to land on a platform out in the ocean, and it didn't quite make it. It was pretty close, but it didn't quite make it. Since then, they've perfected that too, and they're actually landing these rockets out on barges out in the middle of the Atlantic also. So that's aerospace. Davis Aerospace, that's what we do. Now, we are going to teach you some about rockets. As a matter of fact, in our freshman class, one of the very first things we talk about is a balloon rocket experiment and how to get air pressure. Again, this whole business is how to create and how to manage air pressure. One of the very first things we do in our freshman class is give you an experiment on how we can use air pressure inside of a balloon to lift things up off the ground. Same way the Saturn V did, by putting air pressure, creating air pressure. The Saturn V did it through temperature change, okay? So that's the kind of stuff we talk about at Davis Aerospace. How to create air pressure, how to manage air pressure, how to get into aviation, what your generation is going to be doing in aviation, maybe what your kids' generation is going to be doing in aviation, how we can make a living at it, how do we get started. The place is Davis Aerospace. My name is Rick Orzel. I'm a special instructor there. If you have any questions for your teacher, make sure you get it to the teacher will get it to me, and I'll answer your questions. That's not a problem, okay? Bernoulli's principle, that's the key to everything. And if you come to Davis Aerospace, we're going to be talking about that a lot. I'm going to give it to you one more time right now. Increase in velocity causes a decrease in pressure. A decrease in pressure causes the temperature to go down. And the opposite is also true. So increase in velocity, decrease in pressure, decrease in pressure, decrease in temperature, and the opposite is also true. That's the secret right there. I've just given you guys the secret of the universe, okay, when it comes to aerospace and aviation. But there's a lot more that we're gonna tag on to that. A lot of the language, a lot of the definitions, a lot of that stuff. Davis Aerospace is the place. Thank you very much. Next video is going to be on how we manage all this air pressure. And then the last video is going to be kind of a summary of everything. Thank you very much. Look forward to seeing you in the next video.